Okay, section 8.1, part 2. In the last part of the section, we were defining and using sequences. Today we take that a step further and add in the idea of a series. So our objective for today is to sum the terms of a sequence to obtain a series and use summation notation. So right there in the objective, it kind of hints at what a series is. A series is the sum of a sequence. So when we add up so many terms of a sequence, we call that a series. Okay. For example, let's look at the sequence 2, 4, 6, and 8. When I add them, 2 plus 4 plus 6 plus 8. Okay. When I add them, that is now a series. It was a sequence when it was just a list of numbers, and now that we add them, it's a series. Okay. A series can be both finite, as in this case, where I'm just adding 2, 4, 6, and 8, or it could be infinite, where if I was to add 2 plus 4 plus 6 plus 8 plus ... keeps on going for forever. Okay. We have a shortcut way of writing series, and this is what we call summation notation. Summation notation kind of sounds like something that would be on Schoolhouse Rock. Summation notation. Okay, and it uses the Greek letter sigma. So therefore, it's sometimes called sigma notation. It uses the capital Greek letter sigma. So sigma looks like, that. Okay. So if I wanted to add, I'm going to rewrite this in sigma notation. To use sigma notation, you need to know the rule. So you need the rule for the sequence first. Okay. So let's look at our rule for this sequence here. So again, when I put in a 1, I get out a 2. When I put in a 2, I get out a 4. When I put in a 3, I get out a 6. So this is what we did in our last notes. This is the 2n. So this sequence is the 2n sequence. So this is a sub n equals 2 times n. Okay. So to write this in summation notation, okay, I'd write a sigma sign. Okay. So there's my sigma. Mine isn't as pretty as the books are. That's just how I draw mine. Okay, so we do a sigma, and then we would put the rule here on the end. So it's 2n. And I want to add those, and then we put in little letters down here, n equals, and we want to go from the first term, and we want to add all the way up to the fourth term, in this case, 1, 2, 3, 4. So I want to take this sequence and add it from the first term to the fourth term. Okay. Okay, our index, the variable here, this n, is what we call the index of the summation. We call the 1 the lower limit of the summation, and guess what the 4 is? The 4 is the upper limit of the summation. Hey, sometimes for an index, your text uses the letter I, so they would have this written as the summation of 2i from I equals 1 to 4. Okay. See if you can't think of a reason why I might be a little confusing. Okay. So go ahead and jot that down, why I don't use the letter I. I use the letter N. Okay. But then that's completely up to you. I'll do some of the I stuff like the book does, just so we're consistent with the book, but I tend to use N. But you could use really any letter you want. You could use K, you could use A, you could use X, whatever letter you want to use in there. We tend to use letters other than X when summations, just because X's are kind of reserved more for just the algebra type stuff. Okay, and then if I wanted to do an infinite series using summation notation, again, I'd use the sigma, and then I would again use 2n, but now I would have n go from 1, but it's not going to end, so we would write infinity up here because it goes on for forever. So that would be an infinite series. Okay. So to be able to write a series using summation notation, we're here in example 4. We want to write each series using summation notation. The first thing I need to do is find the rule for the sequence. So I need to find the rule for the sequence. Okay. So we practiced some of that yesterday. Again, some of it's kind of hit and miss. You just kind of have to, we'll learn some other tricks for helping to find that rule, but for right now we just have to notice a pattern. So when I put in a 1, we get -1. When we put in a 2, we get 2. When we put in a 3, we get -3. When I put in a 4, we get 4. Put in a 5, it looks like the signs are changing every other, but the number's the same. Okay, so I think I would have n, but the sign's changing every other. So if I put a negative in front of it, but then I'd have -1, -2, -3. So that doesn't alternate signs. So I have to think of what alternates signs. What if I take -1 and I take it to a power and I do an exponential to the n? Let's see, because -1 to the first is -1. -1 to the second is 1. -1 to the third is -1. Hey, that alternates. Hey, and that works because the first one's negative and then positive, then negative, then positive. So I think it's going to be -1 to the n times my n to keep it from always being 1. Because if I didn't have the n there, it would just be -1, +1, -1, +1. The n brings in the actual number. So let's try it, make sure it works. So if I put a 1 in here, I'd have -1 times 1, which is -1. When I put in a 2, I'd have +1 times 2, which is 2. I'd have -1 times 3, -3. So it looks like it works. So there's my rule. My a sub n equals, we'll ignore that there, right there. My a sub n equals -1 to the n times n. So now to write this in summation notation, I'm going to need my sigma and my rule, -1 to the n times n. And we're going to go from n to 1 to which term? Which term would that one be? Since it gets 40 and the number seems to match, it would be from 1 to 40. So there I am in summation notation. So I want to take this sequence and add it for the terms from the first term to the 40th term. Okay. All right, part B. Okay. So write each series using summation notation. Again, I need to find the rule for the sequence. When I put in a 1, I get it a 1. When I put in a 2, 4. When I put in a 3, put in a 4, get out 16. Okay, what I'm noticing here, 2 squared is 4, 3 squared is 9, 4 squared is 16, and I could write this over 1. So to me it looks like it's 1 over n squared. Let's try it. 1 over 1 squared, 1 over 2 squared, 1 over 3 squared, 1 over 4 squared. Hey, that worked. That one wasn't too difficult to find. There's my a sub n. So now to write it in summation notation, I write my sigma, and it's for 1 over n to the second. And I want to go from n from 1 to, well, dot, dot, dot for forever, so infinity sign. All right, so now that we know how to use summation notation, how to write summation notation, let's actually use it. Let's actually find some sums. Okay, so we want to find the sum of 4k minus 1 as k goes from 3 to 9. So now all we do is we plug in the integers from 3 to 9 and add them up. So I'm going to plug in a 3. 4 times 3, 12 minus 1 is 11. So that's my 3. Now I need to do 4. 4 times 4 is 16, minus 1 is 15. Okay. And then I need to do my 5. 4 times 5 is 20, minus 1 is 19. Plus my 6. 4 times 6 is 24, minus 1, 23. Plus now my 7. 4 times 7 is 28. Minus 1 is 27. Put my 8 in. 4 times 8 is 32. 32 minus 1 is 31. And then now put my 9 in. 4 times 9 is 36, minus 1 is 35. Now we just add them all up. So let's see. How do we want to add? I'm going to add things that are nice to add. I'm going to add the 11 and then the 11 and the 19, because 9 and 1 make 10. So that would be 20, 30. Plus, I'm going to add the 15 and the 35, because 5 and 5 make 10. 30, 40, that makes 50. Then I'm going to add the 23 and the 27, because 7 and 3 make 10. 20, 40, That'd be 50 also. And then I'm going to add the 31. So 50 and 50 is 100. 30 and 31 is 61, so we get 161 is my summation here. Again, you could type it in 11 plus 15 plus 19 plus 23 plus 27 plus 31 plus 35 on your calculator, hit enter, you should get 161. Okay. All right, let's look at another summation that I don't have here. Let's sum n from n equals 1 to 100. Okay. So you have to think of what this is asking here. This is asking me to add. My rule here is quite simple. When I put in a 1, I get out a 1. When I put in a 2, I get out a 2. So really what I'm adding is 1 plus 2 plus 3 plus 4 plus dot, 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 dot. Okay. There's actually a really funny story that goes with this summation that has to relate to Carl Friedrich Gauss. Okay. What he noticed is if I'm adding this plus all the way to 100, okay, what he noticed is if I add the first and the last term, the 1 plus the 100, we get 101. But if I add the next term and the next to last, that'd be 2 plus 99, which is also 101. Okay. If I add the third term plus the one before that, again, I get 101. So he noticed there's a bit of a pattern here. I'd actually add 101 50 times because there'd be 100 numbers, each of them would pair up. So I would add that 50 times. Okay, so we actually noticed this, and there was actually a really funny story that went with it. And what I'd like you to do is I'd like you to go to this website right here, storyofmathematics.com, so that's 19th Gauss. That's his name, Carl Friedrich Gauss. And read up a little about Gauss. We're going to talk about him in class tomorrow. Go ahead and share out anything interesting that you have found. You can also do a little bit of Google search. Google him. Okay. You're in front of a computer right now. Go ahead and Google him and see if you can find any interesting information. He's quite a well-known mathematician, and we give him credit for a lot of things. Go ahead and see if you can find some stuff that we give him credit for. Okay, so we'll talk about him more tomorrow. But from his first... when he first noticed this, he actually noticed this at the age of 7. He was quite advanced for his age, to say the least. He attended university in his teenage years. Okay, at the age of 7, he noticed this. So from his original noticing of this, then we have actually some shortcut ways, because it gets really tedious to add up a bunch of numbers over and over and over again when we can notice a pattern. So we have some formulas here for some special series. Okay, first of all, here if I'm just adding, if my sequence is 1, meaning this is my sequence, 1, 1, 1, 1, dot, dot, dot. Boring, 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 boring. Okay, if I'm adding 1 plus 1 plus 1 plus 1 plus 1 plus 1, if I'm adding them as my series, all I have to do is figure out how many ones am I adding, and if I'm adding n of them, then that's what I get. So, meaning if I'm adding, and my sequence is 1, and I want to add from 1 to 10, this is just going to be the 10 because I'm adding 10 ones. Okay. All right, here, this is the sum of the first n positive integers. So this was like Gauss's situation. If I have the sequence 1, 2, 3, 4, 5, dot, 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 okay, I start with taking the number of things I'm adding times the number of things plus 1 and divide by 2, because there's going to be half as many of them. So, and we'll look at this again when we talk about Gauss a little more in class. Okay. And the sum of the squares of the first positive. So here my sequence is I squared. So like 1, 4, 9, 16, dot, dot, dot. If I'm adding up all the squares, okay, I take the number of squares I'm adding times the number of squares plus 1 times 2n plus 1 and divide by 6. This is a slightly more involved explanation for the sum of the squares, so we'll just kind of take the book's word for it that works, okay, because it is quite a bit more of an explanation. Okay, so here's one way we can use this. We can use our sum of n terms. As part of an experiment, a teacher gives 1 paperclip to the first student, 2 to the second student, 3 to the third student, and so on, until the 25th student receives 25 paperclips. So if you look at what she's giving away, we want what is the total number of paperclips that the teacher gave to the student. So we're giving 1 away, then 2 away, then 3 away, then 4 away, then dot, 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 all the way up to 25. And we want to sum these. We want to figure out the total number. Okay, so this is just, again, my rule for this sequence would just be n. Because the first term is 1, the second term is 2, and so forth. Excuse me. So I'm actually summing, I always do that, I'm summing from 1 to 25 of just the sequence n. So then I can use this right here. So to do that, I would take n, which in this case is 25, times 25 plus 1, and then divide that by 2. Okay, so if we take 25 times 26 and divide it by 2, you actually end up with 325. And this would be paper